Thanks for the introduction, Randy, and thanks for coming out. Is this working with the microphone? So let's keep this really interactive. If you guys have any questions, feel free to interrupt at any time. I wasn't entirely sure what to prepare because I don't know exactly what you're most interested in, but we work on a lot of things related to imaging, mostly optimization-based image reconstruction, things like that. Today, I'm going to talk about light field imaging and display. I don't know how relevant that really is for you, but feel free to stick around also after if you're interested in just chatting about imaging, image optimization in general. So for me, this idea of computational imaging is really this intersection between signal processing, optimization, and optics. So we work mostly on geometric optics, but also for all the microscopy projects, we use wave optics models, but we don't really dive down too much into the E&M. But this bridge between signal processing and optics is something that can be very powerful because a lot of the traditional trade-offs that you have in designing purely optical systems, by adding another layer on top of that, you can make different trade-offs. There's no magic, but computation is certainly important. So this idea of computational imaging is basically co-designing optics, sensing, computation. If you have a particular task, a particular algorithm, what's the best optical system for that particular algorithm, for example, right? So that's an idea that's been around for a while already, and people have been using that for coded apertures in X-ray, in the consumer electronics industry, which is what I'm mostly working on. We've been seeing things like high dynamic range imaging coming out. I don't know if you're aware of this. That's a technique where you capture multiple photos of the same scene with different exposures, and then you computationally fuse them into a single image that has a much better contrast, right? And that's something that's on pretty much all of the phones implemented now. So if you open the HDR Plus application, it's on there. There was, a hot topic in the research domain about 10 years ago, but also ideas like super resolution, extended depth of field, so being able to take a picture that has all different depths in focus at the same time. Of course, light fields and compressive imaging are all topics that are, of interest in this computational imaging realm. And we've seen a lot of products coming out. As I said, we mostly look at, problems in consumer electronics, computer vision, and computer graphics. But a lot of these concepts probably have applications also elsewhere. So what we've seen in terms of products coming out is, phones and surveillance systems using high dynamic range. That's important probably for a lot of other applications also where you have, really bright objects and really dark objects in the scene, and you want to be able to resolve both of these at the same time. Then super resolution are things like, I don't know if you've seen this light camera. It's a startup company down in Palo Alto. They're building this thing that's about the size of a cell phone with 16 cameras, and all the cameras have different fields of views, different resolutions, and they claim they can basically stitch a single 50 megapixel image together out of all these 18 megapixel sensors. So it's quite interesting to see what's coming out. Then Ricoh has a camera for extended depth of field. Say if you want to read barcodes at all different distances, you don't want to have one focal plane. You want to make sure that can be in focus everywhere without having to refocus the camera. And then in terms of light fields, many of you probably know the company Lightro. That was a startup out of Stanford. The idea there is to put a microlens array on the sensor to capture the light field inside the camera and enable you to do 3D imaging, refocus, and other things after the fact. I would say this idea of light field imaging is now moving more towards virtual reality, so cinematic virtual reality where you use an array of cameras, like Google's Project Jump here, where you have 16 GoPros in a ring to capture a stereo panorama. So you can later basically put yourself in that environment, but you can turn around and always get a stereo view at any given orientation. So that's something that's really hot in the consumer electronics market right now. Turns out that the same idea of co-designing optics and computation also applies to displays, and that's something I'll talk about also. Here we've seen technologies like high dynamic range displays coming out, but also super resolution displays, extended depth of field displays, and light field displays in general is something that's incredibly important for overcoming traditional limitations like contrast, resolution, and limitations in 3D image reproduction also for displays. So my group does computational imaging, computational display, and light transport in general. We're at this intersection of scientific computing and embedded systems and optics. We've only been around for about 2 years now, so the group is not too big, but the kinds of applications we're working on are in HCI, so human-computer interaction, scientific imaging. We work with SLAC, the linear accelerator, also on face retrieval problems. We work on computer vision problems and graphics things. So what I'll be talking about today is computational optics for near-eye displays. That's something we've been working on for the last 2 years, quite a bit. And then also applications of light fields for fluorescence imaging and microscopy. And there the goal is slightly different. It's getting 3D volume of fluorescent molecules at a high speed and high resolution. We work a lot on time-of-flight imaging also. I'm probably not going to talk about this too much, but here we use custom waveforms and a lot of the techniques that you may know from radar. We can do that now in light, using visible light or near-infrared light for these time-of-flight cameras that, like the Microsoft Kinect and other types of flash LiDAR type cameras that are on the consumer market. These are usually used for gesture recognition and gaming and things like that, but people have been applying them also to robotics and all sorts of other things. And again, feel free to interrupt me anytime. So let's talk about near-eye displays a little bit, because that's quite an interesting space right now. So we've had stereoscopic displays for a long time, since the early 1800s, 1830 or so. We've had these stereoscopic viewers. And if you think about what the consumer products now are, it's the same principles of operations in a way, right? We have a micro display, we have a lens, see a floating image somewhere in space. But a lot of things have actually changed. So a lot of the latency issues have been solved over the last couple of years. So the image doesn't lag behind when you reorient your head anymore. And a lot of other issues have been solved. Who's been able to try any of these displays? Yes, 1, 2, that's it? 3, 4, okay. So basically, Oculus has the consumer product out right now, and HTC has the Vive. It's a really incredible experience. If you haven't tried it, I highly recommend. It's a completely different experience, right? It's not just a bigger image. It's like, especially when it's interactive with the controllers and so on, you can actually do things. So it probably is a new type of a medium, right? But there are a lot of technological challenges still, and some of them we are working on. One of them is the divergence accommodation conflict. That's a conflict in the depth cues that you get. Another one is the vestibular visual conflict. So, for example, you can't jump around in this virtual environment. Think about Super Mario, right? Super Mario jumps around a lot. You can't do that because you don't feel yourself moving. There's a discrepancy between the vestibular system, the sense of gravity, and the visual cues, so people get sick, right? Actually, we found these pills online that are specifically made for VR sickness. I mean, I don't know if that's really serious, right? But probably not. But yeah, people are very concerned about comfort in general. And divergence accommodation conflict is something that we work on a lot, and that's something I'd like to talk about a little bit more. Augmented reality is also something that's coming, but there are a lot of more problems. So are you aware of the difference between virtual reality, augmented reality? So VR is when you stick the display in front of your eyes and you're completely immersed in that environment. And augmented reality is when you still have a beam splitter or some type of a combiner where you see the real world, but then you get images superimposed. And that's very challenging to do because you need to be able to get the lighting right, you need to know the geometry, you need to track your eye, the environment, you have to do all of that in a really small form factor. And some of the companies that got a lot of funding recently, like Magic Leap and HoloLens and others, Microsoft, are really pushing towards this. But VR is what we have right now. So now, to understand some of the challenges on the optics side, we need to understand the human perception to really grasp what's going on there. So if you think about depth perception, there are many, many different cues that the brain actually uses to see 3D, and many of them are already supported by two-dimensional displays, like the projector, like perspective, occlusions, shading, and all these things are already supported here. But there are 4 cues that you see on this slide that are very important to be considered for near-eye displays. So this is binocular disparity, the fact that you see 2 different images with your eyes. That's pretty straightforward, and that's a visual cue, but it drives the oculomotor cue, which is vergence. So vergence is the relative rotation of your eyeballs in the sockets, and these cues are usually working together. Now, there's another cue, the focus cues. That's a monocular cue. So in each eye, we have a depth of field effect on the retina, and our lens, the crystalline lens in the eye, can accommodate at different distances. I mean, the ability to accommodate kind of decreases with age. So over the age of 40 or so, people can't really accommodate that much anymore. But keeping the same kind of focus cues in mind are important to not only provide visually comfortable experiences, but also accessible experience. So you want to see an image, a sharp image in general. So here's what happens in the real world for most young people. They verge and accommodate at the same distance. So if you look at something that's close, the eyes will verge inward or rotate inwards, and the eyes will always focus at the same distance as well. So these cues all match and work in harmony. When you think about a near-eye display, the near-eye display basically has a magnifying lens, a micro display here, and what you're looking at is a virtual image at some distance. Usually they put the virtual image at about 1.5 meters or so, because that's a pretty good distance for focusing up to infinity, and you can kind of get a visually comfortable experience for virtual objects that get about this close, about 1 meter, 75 centimeters or something like that. Right? But the focus of your eye will always be driven towards this plane, because you're just looking at a floating image in space. So now what happens is that by rendering these stereo image pairs, you can verge to the correct distance, because you can generate the disparity cues by rendering a stereo image pair, but you can't really change where the eyes are focused because it's optically fixed. Right? Does that make sense so far? Yeah. So now these cues mismatch, and our brain gets mismatching cues from different sensory systems, and that is what usually creates discomfort. Maybe by evolution, when things don't match, then the body probably assumes that the body's poisoned or something like that, right? That's also what happens in motion sickness. So when you drive in the car and you get motion sick, there's a different discrepancy between the visual cues, what you see, and what your sense of gravity feels. Right? So if you read a book in the car, then your body feels that the road is bumpy, but the book moves with your eye, so you don't see that it's bumpy, right? And then some people get sick, not everybody, but same in this case. So we came up with this idea of building a new type of a near-eye display, and we called it a light field stereoscope instead of the stereoscope. And the idea is really to emit a 4D light field to each eye. So this was the prototype that we built in 2015. We just 3D printed the housing and changed the optics, and it's really driven by computational optimization. The hardware is very similar to a conventional near-eye display. Basically, you have a backlight here. Can you see this? Yeah. Backlight here. We use LCD panel, although most consumer electronics companies now use OLEDs because they can switch faster. There's a bit of a spacer, about 6 millimeters, and then there's a second LCD panel here. So we basically have 2 planes inside the display, and then we have the magnifying optics in front of it. So you see 2 planes, but the goal is not just to show 2 planes where your eye can accommodate at these 2 planes. The goal is to be able to create this full light field entering your pupil. So instead of creating a stereo image pair, where you get one image with the right eye, one image with the left eye, we now want to get many different images into the pupil, right? So think about the pupil and think about a pinhole. Like, we want to get many different images over all these different positions of the pupil. It sounds challenging, but that's kind of what you need in order to get these focus cues right. So on the right here, you see a target light field where we rendered 7x7 images from slightly different perspectives. They all look the same to you because the amount of parallax in them is very small, but there is a little bit of a change, and that represents all these light rays flowing into your pupil that you kind of want to recreate, right? Think about a hologram or wavefront entering your pupil, and the image that's projected onto your retina will then change, and this depth of field effect will be automatically created. So now, why can we get away with these 2 layers of LCDs? Well, the thing is, these LCDs are multiplicative. So the rear layer here will emit light, and then the front layer can block the light. So along any ray, you multiply these two values because each of the pixels are basically programmable attenuators. Right? We remove the backlight from this front LCD. It's different from having emitters. It's not the same as having a transparent OLED or using a beam splitter where all the lights add together. In this case, it's really this multiplicative effect that creates a nonlinear effect that allows us to potentially get the 4D light field back. So we represent the light as a multiplication along the ray, and then we're trying to approximate the 4D light field using the degrees of freedom that we have by solving an inverse problem. In this case, it's a non-negative matrix factorization problem. And the key is really getting this parallax over the pupil. So the images need to be changing over the pupil. Right? So we developed a lot of matrix and tensor factorization techniques that people have been using for other types of classification problems and so on. We applied them to these problems in near-eye display generation and implemented all of that on the GPU in real time. What we get out at the end, in this case, is still only 2 images. So the input is, let's say, these 47 images that we render per eye. We crunch the numbers, and what we get out is these 2 images that we put then on the LCDs, and they optically overlay. So you can see that it kind of makes sense because some of these objects that are closer towards you are mostly assigned to the front layer. Some of the high-frequency details for these bottles in the back are assigned to the rear layer. But then you can actually focus on both of these. So here's kind of what you see. In a traditional head-mounted display, you see one image either completely in focus or completely out of focus. So right now we're taking a camera with a finite depth of field and we're just refocusing it, simulating what the eye would see. Right? So in this case, either it's fully in focus or fully out of focus. For the light field head-mounted display, we can basically generate this depth of field effect optically. So there's no change in the image in this case. We're just refocusing the cameras. Right? So that's the kind of effect you want to see, where you can focus on the rear objects and the front objects are out of focus, and vice versa. That's really important mostly for young people, mostly for things that are very close. Everything that's within arm's reach, everything you can touch, right? Because that's the kind of stuff where the discomfort is the strongest. Any questions so far?
By 4D light field, you use time and X, Y, Z?
No, so by 4D light field we mean X, Y on the screen, and then you have two axes on your pupil, basically, right? So think about a ray in space being parameterized by its intersection with the screen and then with some point on my pupil, right? So that's a 4-dimensional distribution of light rays that then get projected onto a 2D retinal image that changes with the accommodation state of the eye. But basically what we're trying to recreate is we define the eye box as a 1 centimeter by 1 centimeter region around the pupil so that your pupil could move within that and it can expand and shrink. And basically if we can recreate this light field entering the pupil, your pupil can do whatever it wants. It'll always pick up the right rays and create a realistic image. Yeah. So that's the 4th dimension. Then if you add time, it's 5. Yeah. It's pretty challenging to do this really fast because now the computational overhead is very, very high. Instead of rendering 2 images, you have to render, we usually do 50 images, so 25 for each eye. Think about it as a small camera array around your pupil. So you have 5 by 5 cameras here that all render an image, and then you run the factorization technique, which takes some time too. And it's an interesting approach, but the question is how much do we really need to create a visually comfortable experience? So then we said maybe we can do something very simple. People have been doing things like high dynamic range images where you capture, let's say, 2 images with different exposure, fuse them together. Maybe we can do something like that too. So we found a technique that people use in ophthalmology to treat presbyopia, which is called monovision. So for presbyopia, most people get bifocals, right? So you look up, you see far, you look down, you have the insets, and you can read. But many people actually use a different technique called monovision, where you put each eye at a different plane. So usually the dominant eye is corrected for far vision, distance vision, and the other eye is then corrected for near vision. So you could switch your dominant eye depending on what you're looking at. Is anybody using that, monovision? Yeah, couple, 2? Okay. So now the idea isn't new, But we wanted to try and see if that makes any sense to use techniques like that in virtual reality also. So we built a prototype by using these focus tunable lenses. So we can change the shape by putting current in and program the focal length of the lens. So we can place the virtual image at any distance we want. For example, farther away, closer, but also at slightly different distances for each eye. And we wanted to test a couple of different display modes. So this is something that people haven't really published about. And we wanted to see if it makes sense at all to change these focal planes or put them at different positions. So we tested a couple of modes. There's a conventional mode. In this case, the virtual image is at one fixed distance for both eyes, and you're looking at objects that are at different distances. We tried a technique where we just render the depth of field into the scene. So that's a software-only approach. We just render depth of field effect into the image. So that then we said, okay, what if you had eye tracking? You could just put the virtual image wherever you're looking at. So if I look at you, you're close, put the virtual image right there. Look at you, you're farther away. I'm just gonna change the focal length adaptively depending on what I'm looking at. And that's really interesting. The virtual image is defined by this Gaussian thin lens equation. I mean, probably everybody knows that. We can change the focal length in this case. But alternatively, we could also actuate the display inside the screen and get the same effect. Okay. And then we tested Monovision, where Monovision is a little bit weird, right? It sounds awkward, but it's actually something that people get used to quite quickly. In this case, we put the right eye at a distance, the left eye closer by, and then the idea would be that you can look at different virtual objects and your accommodation will always be driven by one eye or the other depending on what you're looking at, because they're coupled, right? So you can't have your eyes accommodate at different distances. They would either both accommodate far or both accommodate close. The question is, can one eye drive it and then the other eye? And what we found is that it works pretty well for people who don't have a really strong dominant eye, because then it's difficult to switch. So we did a user preference study where we show people a couple of different scenes and ask them to rank them. And what we found is that software-only approaches don't do anything, which makes sense because even if you blur the image on the screen, your physical accommodation is still going to be at that plane. If we change the focal length of the lens adaptively, depending on what you're looking at, it makes a huge difference, and it's statistically significantly better than the conventional mode. Monovision was a little bit better, but not in a statistically significant manner. So that's interesting. Then we ran a couple other user studies and looked at performance for specific tasks. We ran a task where we tested visual clarity. Visual clarity means you put a small target on the screen and you ask the user to say which orientation the E is on. We randomly oriented at different orientations.
So when you say adaptive focus, you're actually mechanically moving?
So we're not mechanically moving anything. We have these liquid lenses, so we can program it into the lens. We can change the focal length, which is equivalent to using a static lens and actuating the screen. But for us, it's much easier because we can randomly switch between all these different modes. The user doesn't know what he's looking at, and we test them. Yeah, it's pretty much no latency. These lenses switch at about 15 milliseconds. The accommodation system takes about 100 to 300 milliseconds, so it's order of magnitude faster. Yeah. And that's probably something we'll see. I have a slide on that later, but I think next generation near-eye displays, we're going to see eye tracking integrated and then either physical actuation or some other technique that can change the focal plane a little bit while you're running it. Yeah. So it's much better. So basically here we tested a couple of tasks, detecting small targets, detecting if one object is in front of the other without having any occlusions or anything. And what comes out is that this adaptive mode is really makes people react much faster, much more accurately. So that may be important for time-critical tasks. It's also more comfortable, and people can judge relative depth much better. So overall, there's a lot of ways to improve these near-eye displays. So what we're going to see, and that's something we're working on with a bunch of industry collaborators right now, is basically adding eye tracking to the head-mounted display, and then probably actuating the micro display is better for a consumer product because the liquid lenses are pretty small. And when they're small, the field of view is restricted for your eye, so you can only see a small part of the image, whereas it's really important to get this wide field of view for all of this near-eye display stuff. Yeah, so we'll probably see that coming out, and it's kind of interesting to think about, computational optics for near-eye displays. I mean, I don't know if that's something that you've been thinking about a lot, probably not, but there are a lot of applications for things that you may have heard of, like point spread function engineering. It's something that people do for microscopy. You can do the same thing for near-eye displays also. So here's our setup that we have right now. We have a couple of photographic lenses with these 2K LCD displays on the side. We have the programmable lenses in the middle. And then in this case, we have a mirror. But right now, we actually have beam splitters here. And then there's a big device behind it, autorefractor, so we can actually measure where people are accommodated. So it's very interesting to see how we can engineer the point spread function in these displays also to give you better visual experience in general. So a lot of the techniques like extended depth of field and so on are also important for near-eye displays. And maybe that's the connection. So I was just teaching in class actually that finished last week. So here's lab 3, where we have the students put together a head-mounted display also from scratch, mostly undergrad and early master students. But it's a lot of fun for the students right now. And we can use things like virtual reality as a vessel to teach them about signal processing also and get them really excited about that kind of stuff. So one thing we do, for example, in class is we have a little IMU and an Arduino, and they implement all the sensor fusion on the Arduino. So it's a really fun way for students to get them excited about the signal processing and the optimization, and teaching them in a hands-on manner. So let me talk about light field imaging also, in particular at the diffraction limit, because that's something that's, of course, very important. So as I mentioned earlier, probably you've seen this Litro camera. This is the second generation. It's called the Illum. It has a 40 megapixel sensor, and then it has a microlens array on top of the sensor to pick up the light field inside the camera. So now it's the same idea, but reversed, right? Before we were thinking about shooting all the light rays into the pupil. In this case, we want to capture all the light rays inside the camera. So the biggest challenge for light field photography is the resolution, because you slap these microlens arrays on the sensor, and the resolution is much lower right away. Have you guys been thinking about these microlens-based systems, wavefront sensors at all? A little bit? OK. So there's a fundamental trade-off between spatial resolution and angular resolution. We can also use the whiteboard, maybe? No, whiteboard. OK. The idea is to capture all the rays inside the cameras with these microlenses, but the resolution limit is terrible. And that's probably why the first and second generation of the Litro wasn't really a success in the consumer market. So we've been thinking about coded aperture type approaches to overcome the resolution trade-off and get high diffraction limited resolution. So here's the idea, okay? You have a scene, and you think about whatever comes out of the scene as a set of rays. The rays enter the camera with a finite aperture, and you want to capture all these rays on the sensor. So normally, the sensor would integrate over all the rays coming in at different angles, and we want to be able to resolve that information and not only store the intensity per pixel, but also the intensity per direction of arrival, right? So that's basically the light field. And again, it's a 4D function, x, y on the sensor, but then also the angle, theta and phi. Most people do that with this microlens array. You basically mount the microlens array at a small offset in front of the sensor, such that each pixel on the sensor is in focus with the aperture. And then each point on the microlens array is in focus with the scene. So you're trying to chop up this 4D space and multiplex it on a 2D sensor. Right? Does that make sense? You have microlenses. They're about maybe 20 microns or so. Cell phone camera pixels are about 1.5 microns. So you get about maybe 14 to 17 pixels or so underneath each microlens. You get 14 times 14 pixels under each microlens. And that gives you, that samples the aperture at these 14 by 14 different locations, right? You could alternatively capture this light field by taking a pinhole and moving it around in the aperture and capturing a single image every single time. It'll give you slightly different perspectives of the scene. But the parallax only changes over this area, right? Like the size of the aperture. But that contains a lot of information, a lot of useful information. Right? Yeah, so that's equivalent to basically sequentially capturing these images with a shifting pinhole in the aperture itself. And this is kind of how a light field looks like. This is computer generated, but it's actually a 2D light field corresponding to the scene that I just showed you. This is like a dragon and some bunnies here. It's rendered with a ray tracer. This is how a light field looks like. X is the location on the sensor, and V in this case is the location on the aperture, right? And for in-focus objects, they won't change a lot because all the rays coming in at different angles on that pixel will be the same. So that's an in-focus object, and then objects that are out of focus, they will have this kind of a shear. So it's interesting to look at these high-dimensional visual signals. The light field is actually 4D. We're just showing you a 2D slice here, but there's a lot of interesting signal processing you can do on these high-dimensional visual signals. One thing that we've been looking at is how can we overcome this resolution trade-off between spatial and angular resolution. So again, the resolution trade-off is this. You can choose the microlens size, and you can make it bigger, then you capture more angles under each microlens, right? You can choose twice as big of a microlens, and then you have more samples of the aperture, but the spatial resolution is defined as the number of microlenses. So there's a fundamental trade-off between, you want to make the microlenses as small as possible, have as many pixels underneath as possible at the same time. So how are you going to do that? It's impossible. And the fundamental limit is the diffraction limit in this case, because even if you could make a microlens that's extremely small and still have pixels that are very small underneath, you won't be able to resolve any of that information because it's under the diffraction limit then. So we came up with a different idea. We modeled this point spread function of the aperture as using the Wigner distribution function. We can describe the amplitude and phase in the aperture, so using standard techniques, and then use the 4-dimensional Wigner distribution function. Has anybody heard of that before? Yeah, a couple of people. So it's actually the same thing as the light field. It's a joint representation of space and spatial frequency, so space and angle, except that the light field doesn't account for diffraction, and the Wigner distribution function does. So, but we can find a connection between the two, and if we do that, then we can actually model the effect of the diffraction here. And one thing we can immediately say is that if we use a large aperture, of course you get high spatial resolution because, you have a large aperture, but you have no angular information whatsoever. You can use a small aperture and get a really high angular resolution, but now the spatial resolution is low. And that's the same as the uncertainty principle, right? You can try to isolate one axis, but by giving up all the information on the other axis. Or you can do it the other way, but you can't get both at the same time. And so we thought, maybe we can get both at the same time by capturing multiple images and making different trade-offs for each image, and then computationally fusing them. So then our idea was, okay, we can probably capture a small pinhole aperture on the outside and then make them bigger and bigger so that we get the high in-focus diffraction-limited resolution, but we get the large depth of field from these pinholes on the outside and the parallax at the same time. So it's kind of like this. We can capture the large aperture image, so we can get high diffraction limited resolution for the in-focus plane, but there's no information from the out of focus areas, or we can stop down the F number and get medium resolution for both. It only makes sense for diffraction limited systems. Like if you get, if you have let's say a camera that doesn't have a diffraction limited performance, then you just capture the large depth of field and you're good, right? But it's quite interesting because we can use computer tomography and other more complex inverse methods to really fuse the data back together. It's slightly beyond the scope of the talk, but a lot of computational methods are actually needed to do that. So here we did a more extreme comparison between what you can get with this variable aperture resolution and fusing the data computationally and the conventional pinhole approach. So that's really interesting. We built a small prototype that just uses a conventional SLR camera with a programmable aperture where we can program the slit and translate it. And that was interesting, but where it's really going towards is this idea of fast, high-resolution 3D fluorescence microscopy, because that's what people care about, really. Yes, question?
To work around the limitation of measuring angle and resolution at the same time, could you use a beam splitter to look at two separate detectors, one with the translates to the other resolution?
Yeah, that's a great idea, right? Oh, so the question is, couldn't you use a beam splitter, have a high resolution sensor on the one side and then a Shack-Hartmann sensor on the other? And that's certainly true. In that case, you're capturing two images with a lower photon count for two particular choices of this spatial angular resolution trade-off. So you get the full diffraction limited resolution for the 2D sensor image, and you get one particular choice of the spatial angular resolution trade-off for the Shack-Hartmann sensor. So with the coded aperture approach, you can kind of capture multiple different trade-offs at the same time, and the degrees of freedom for the design are a little bit higher. I mean, if you know that all the information in the angle are captured with your Shack-Hartmann sensor, and you have all the in focus high resolution, then you're probably done, right? So there are different ways of doing that too. But now you're also splitting up the photons. We do that too, of course, because we have an amplitude mask in the aperture also. So what we're really going towards is multiple phase coded apertures that capture most of this information in a very photon efficient way. But there are many different ways of achieving similar things. Yeah. So this is a video of a volume of neurons captured in the mouse brain using a technique called clarity. Carl Deisroth at Stanford invented this. Basically, you have the mouse brain, and you wash out all the lipids. Right? The lipids are what's actually scattering, and then you can use techniques like light sheet microscopy or other types of microscopy techniques to capture the neurons. So they're still intact, the structure is intact, but of course they're not functional anymore. So now if you want to do that in vivo, you need to have fast and high resolution 3D techniques, because all of them are oriented in a three-dimensional structure. The challenges are, or let's say the properties of fluorescence in this case, are that first of all we model it as isotropic, because usually you look at clusters of molecules, even though one individual fluorescent molecule may be not isotropic. Whatever we're looking at is mostly isotropic. They're incoherent with one another, but they're coherent with themselves. Right? So if you have one emitter, it will still obey the diffraction limit as it propagates to the sensor, but 2 points interacting with each other will only add in intensity, but there's no phase interaction between these points. The challenge is that we have low signal now, so we want to capture as many photons as we can. A couple of years ago, we had a collaboration with Ed Boyden, actually, at the MIT Media Lab, where we applied light field, the idea with the microlens arrays, so Shack-Hartmann sensor basically, to 3D fluorescence microscopy. In this case, we looked at things like C. elegans. That's a little worm. It's about maybe 100 microns long, has 300 and a bit neurons, well-defined. People know exactly the structure. It's completely transparent, so we can do in vivo experiments without actually modifying the worm. I mean, it's genetically modified already so that it exhibits the fluorescence. But what we're looking at is individual neurons that are glowing here, and the neural activity will change the relative fluorescence. Right? So if we look at the change in relative fluorescence, we can look at the individual neuronal activity traces. So we built the scope, and it's a very similar design to the microlens-based camera. We have a microscope objective here, a three-dimensional sample, the illumination here, and then in the detection path we have this microlens array and an SCMOS camera. What you capture are these images with these microlens-based images that I showed you also earlier. That's kind of what comes out of the scope. And then to get the 3D volume back, you actually have to run a computer tomography reconstruction, because you're capturing multiple projections through this 3D fluorescent volume, but you want the volume back, right? So that's the light field, these projections. Does it make sense so far? So that's probably also more relevant to some of the things that you guys are working on. And then at the end of the day, you get a volume back. In this case, we were able to image the entire animal. So it's a pretty small animal, so it's not that challenging, but nobody had done that before. And you're still doing all these resolution trade-offs. You can see that the resolution is nowhere close to a conventional microscope, but in this particular case, it may be okay as long as you get cellular resolution. You want to be able to resolve individual cells in the volume. In this case, we got about 70 neurons in the head region over a field of view of 350 by 350 micrometers, and in this case, depth of 24 microns. So it's not super deep, but that's about what you get before the scattering comes in too much, right? And we can image that at 50 hertz because you just need a single image per volume, and you can just run the camera at video rates. We also looked at zebrafish larvae, actually, but the neuroscientists in this case are usually interested in looking at the neuronal traces, and they want to analyze the correlation between the neurons. And here's what you then extract over time. These are individual neurons on the y-axis, and then the relative fluorescence in the color, but then here you have time on the x-axis. So that's kind of what we get out at the end of the day. Questions for that? All right. So as I said, we wanted to think about better ways of capturing this because we want to get the full resolution at some stage, right? And you can think about a couple of different architectures that allow you to capture the light field in a fluorescent microscope, and they're all equivalent in the geometric optics limit, but they're slightly different if you consider wave optics. So the idea of using a microlens array allows you to isolate individual rays that in the back aperture plane here, right? This is the back aperture, and one pixel here will capture a projection of the volume from this angle. The next pixel over is going to capture a projection at a slightly different angle, and this pixel over here will capture yet another projection, right? You could alternatively just put an array of small cameras into the back aperture and capture that. In fact, there was a paper coming out last year that actually did that. So a couple of people from Tsinghua University in Beijing actually built this camera array and focused it down into the aperture to capture this light field live of a couple of specimens. You can also use a coded aperture in the aperture plane where you try to isolate again these individual projections, right? But again, the same trade-off is going to happen. If you narrow down the numerical aperture, you're going to give up spatial resolution. And that's something that you can't change even for the camera array after the fact. So the diffraction limit, I mean, you're probably very familiar with this, is directly related to the numerical aperture size. And the wavelength and all of that, of course, too. But let's say the wavelength is fixed and something that we can't change because of the fluorophores, then the only thing we can change is the numerical aperture. So if you want to capture a light field with m angular samples, you're going to reduce the numerical aperture by a factor of m. And so your diffraction limited spot size is going to go up by a factor of m too. And that's usually not desirable. So interference is something that is well known, and that's something that we'd like to exploit. So the question is, how can we design coded apertures that give us the 3D information, but that also allow us to use interference of one emitter with itself on the sensor, so we get, high diffraction limited resolution. So here's an illustration of the problem again. This is what the conventional light field would do, which is what we did and a couple other folks at Stanford also. If you sequentially scan a pinhole over the aperture, you basically get a point spread function that looks like this in x and z, right? So this is lateral and axial point spread function. These are also the projections you will get. Each image would give you a projection at that angle, but the waist of the Gaussian beam in this case gives you the highest possible resolution that you can resolve. The optical transfer function looks like this, and compared to the toroid that is basically representing the bandwidth of the objective, you're only scanning a very, very small part. If you had an unlimited amount of time, the best way of capturing this is you just take two pinholes and capture any possible combination of pinholes. That would allow you to get the highest diffraction limited resolution and all the 3D information at the same time. You still have to computationally reconstruct it, right? You capture these individual frequency components every single time. Does this make sense? But you're basically scanning out the entire 3D bandwidth of the objective. But it would be prohibitive in terms of number of images if you actually want to capture anything fast. So this may be very interesting for things like polarization or things that don't move very fast, right? If you could just scan combinations of pinholes. But the idea of pairing these pinholes is actually very powerful because you get the interference.
So what's the speed relationship to the moving object and your scan speed?
Yeah, I mean, that's a good question, right? If you have something that doesn't move, then you can take as many images as you want. But if you have something that's only there for fraction of a second, then the requirements are, you need fast imaging. So for the fluorophores that we're looking at, you need at least about 10 hertz or so, 20 hertz, and they're getting faster. And people are now also switching to voltage indicators that are even much faster. So it's important to keep the frame rates pretty high. Does that answer your question at all? Or? Yeah. So we need at least 10 frames per second about, because the calcium indicators we've been working with are about that speed. I mean, the fluorescence lifetime is pretty long, so it's not great, right? But if you have a camera that captures at 100 frames per second, looking at something that only changes at 10 hertz, I mean, you can capture 10 images maybe in that time. And you still give up photons because you're chopping up the time. And eventually, everything is photon limited, right? I would say. But in this case, let's say we have the degree of freedom of capturing a few images, and we try to get the best out of those images. And we tested a couple of different scanning schemes for that, something in the order of 10 to 20 images. In this case, we're looking at the numerical aperture here, and we tested the pinhole approach, where you scan a pinhole over the aperture. We tested the circle approach that I showed you earlier already, where we capture the small pinholes from the side, from the steep angles, but then we capture the full NA from the center. And then we tested a couple other things like these rings too, because that's more like a Bessel beam then. That gives you extended depth of field, but at the cost of losing photons. And what we found is that, of course, the scanning approach, just like in the 2D or in the computer vision kind of an application earlier, gives you much better resolution than the conventional pinhole scanning approach. So if you think about Shack-Hartman sensor by itself, would give you this, and the scanning approach with variable aperture gives you something much better. I mean, it's obvious, right? Because especially in the focal plane. Outside of the focal plane, you get about the same. So it doesn't help you much for out-of-focus things. But for the in-focus things, resolution is much higher. I mean, you can always use focal stacks or other types of techniques. And those would give you a better resolution if you have the degree of freedom of actually changing the focus very fast. Right? And there may be applications where that's not the case. And all of these considers constant illumination. So if you can use structured illumination, you can get much higher resolution, of course, and there are many other design choices that you could do. But in general, I think it's interesting to think about coded apertures still now, maybe 40 years, 50 years later, because they have interesting applications in many different fields, not only in microscopy, computer vision, but also in near displays, virtual reality, augmented reality, right? I think that's for me the interesting part, that simple tools like thinking about light as something as simple as the light field allows you to design new devices, computational optical devices for different applications. So that's kind of what we do. I'm teaching a couple of courses like digital image processing and computational imaging, where we do a lot of image reconstruction, and this is an introductory course. These are also offered in our SCPD program. That's a Stanford Center for for Professional Development. I don't know if you do that here, but we get a lot of industry folks actually taking courses at Stanford remotely. So you can come to class or you can take it remotely. All the lectures are recorded. Then you can do all the homeworks remotely. Maybe something that some of you are interested in, but we offer that through specific programs. The VR course that I'm teaching now, that's not offered because it's a lab-based class, but a lot of the other classes are offered online. So if anybody's interested, I'd be happy to also talk to you about other courses that are being offered. So thanks a lot for your attention, and I'll be around for a while and open for questions.